In this second video for lesson 4.1, we're going to learn about regression. So correlation can help us to describe the relationship between two quantitative variables in terms of direction, strength, and form. But in order to make real pricing decisions for our Ames housing data, we're going to need to look at the impact of each feature in more detail. The second method to analyze relationships between two variables is regression analysis, where we can move on beyond the basic descriptions and actually write a mathematical equation in order to represent the relationship between the two variables. To help you understand regression, if we go back to our example on sale price and above ground living area in Ames, if you had to place a single line in order to try to capture this positive linear moderate relationship, where would you place it? There'll be different answers, of course. It does depend on personal judgment, but some people try to balance putting the same amount of points above and below. I generally just try to capture the overall pattern in the data, maybe something like this. In order to help see where this line is, let me just make it a bit more bold, and then we can adjust it farther. I would say I'd put it somewhere around here. That it's capturing that positive from lower left to upper right direction. It has a balance of points above and below the line. That's where I think if I had to draw one line to try to capture that relationship in the points, where I would put it. So this is a line that captures the relationship. But where is the best line? If you add a trend line, this is actually where the best line would be that captures the relationship between the points that represent living area and sales price. For this line, it's also in blue, so it might be a bit hard to see. You could also use the formatting tools in Excel to change the color if you would like, so it stands out a bit more. Have to change it individually. Something like that. Again, you don't want to choose the same color. So maybe put it in a green. And we can see that my personal line in orange is not actually the best line, the mathematical one found in green. So the question becomes, how did Excel get this best line in green, and why is it the best line? So that line in the green, that is the best line, is what we call the line of best fit, or it can also just be called the regression line, or regression equation is another name for it. And it is the line that best fits the points. And the reason that it best fits the points and how it is found is if you were to look at the scatter chart, how the line is found is you would look for the distance between every single point and the line. This distance, this vertical distance, is what we call a residual or error. That's why it's called E here. So you do that for every single point in the data set. Find the distance between the point and the line, distance between the point and the line. Then you'd add up all of the errors. Technically, because some are above the line and some are below the line, you'll have the same problem we had with standard deviation, where they would perfectly cancel each other out. So for that canceling not to happen, we square the errors so that they're all positive and they don't cancel each other out. The best line is the one that will have the smallest sum of the errors squared. So that means it has the least error. So the best line is the one that's technically closest to all of the points. In high school, when you worked with equations of lines in grade 9, the equation of the line you probably used was y equals mx plus b, where y represents the slope, that's how steep the line is, and b represents the y-intercept. That's where the line starts from, or you can also talk about it as where it crosses the y-axis. So this would be the intercept where it crosses the y-axis, and the slope is how steep the line is. In statistics, we use a slightly different notation in order to represent the line of best fit. Because y equals mx plus b represents any line, we want the line that has the smallest errors, the line of best fit. For that, we say that y hat, that means any predicted values for the dependent variable, is equal to b1, where b1 is the slope times x, plus b0. b0 is the y-intercept. So basically, we just use all letter b's instead of using the letter m. So B0 is the intercept, where to start from. B1 is the slope. How you interpret the slope in a business context is it will be the change in the dependent variable for a 1-unit increase in the independent variable. The y-intercept will be the dependent y value when the x independent variable value is 0. There's a couple of ways you can find the line of best fit in Excel. You can use formulas. There's a formula called intercept to find the y-intercept, and a formula called slope to find the slope. Also within the data analysis tool pack, there is a regression tool. The regression tool can also find the y-intercept and the slope values for you. Once you have the values of the y-intercept and the slope in this equation, you'll be able to use this equation to make predictions. So that's the goal of regression, is that if we have something like the average or above ground living area in a home, we can use that known above ground living area to predict how much the house would sell for. There are two different types of predictions we're going to talk about. Interpolation is predictions that are within the range of data, and extrapolation is predictions outside of the range of data. We're going to talk about both, but you need to be very careful when extrapolating because sometimes the model doesn't hold outside of your data range. So let's look at some examples, the ones we previously looked at. First, for sales price and above ground living area, how would we find the line of best fit? We need to find our slope and y-intercept. So for the slope, we use the equation called slope. Notice the equation is very specific, that you have to select the y's first and then the x's. So remember, our y we're trying to predict is the sale price, and our x, the independent variable, is the living area for this example. So they have to be selected in that order. And then I would press enter, and I get my value for the slope, 107.13 approximately. For the y-intercept, use the equation called intercept, and again, they must be selected in that order, y's and then x's. The y is the sale price. The x is the living area. Press enter, and I get $18,569.03. So what do these values mean in terms of sales price and living area? Remember, the slope is the change in y for a 1-unit increase in x. So what this means is when above ground living area increases 1 square foot, because the slope is positive, this means price also increases, but by 107.13, the value of the slope. So when you have a 1-unit increase in x, x is the above ground living area. The change in y is 107.13 because that's positive. That means it's also an increase from a positive correlation. The y-intercept is the value of y when x is 0. What that would mean is the price when your house has 0 square feet above ground living area. So I think this is not a realistic situation because I don't personally know of any houses that only have a basement and no above ground area. But that's probably why the price is quite low. That houses also don't sell for only $18,569 because this is not a realistic situation. But even if it doesn't actually make sense in real life, that is still the interpretation of the intercept, the value of y when x is 0. So if x is living area and it is 0, that would be the value of the price. Another way you can get these same two values for the slope and intercept is using the regression tool. So let me show you how to use that one. So I'll go back to my data and go to my data analysis tool pack where I'll find regression. For the Y range, that's the sale price. And you can see again how it's so important to be able to tell the X and the Y variables because it keeps coming back. So the X is the living area. I did select the names living area and price. So because I selected the names, I have to check the box for labels. And then I can put this into a new worksheet. From there, I'm going to copy my summary output into my regression sheet here. This has a lot of information, but the two values you specifically need here are your intercept, the same value we had above, 18,569.03, and your slope. The slope specifically doesn't say slope. It says above ground living area, the name for that variable. The reason for that is to remind you that that is the x variable that the slope is multiplied by. Remember that the equation of the line in statistics is y hat is the slope times x plus the intercept. In this case, what we're trying to predict is the price, and we would say it is the value of the slope, like about 107.13, times x. The x variable is the living area. I'll just call it area for short, plus the intercept, which is 18,569.03 approximately. So the reason it says ground living area is to remind you that this is the number that needs to be multiplied by the area when you're actually using the equation. And that is the final step. The whole reason that we're getting this equation is so that we can use it to make a prediction. One other thing before we make the prediction I wanted to mention is that we'll talk about this next class, what this ANOVA is there for, but some other things you can notice is that the total number of observations is included there, and we also do have the value of R, the correlation coefficient, telling us that this is a strong positive correlation from what we calculated earlier. So now that we've talked about this output, we'll use the output for interpolation and extrapolation. For the interpolation, what that means is we pick a value for the living area that is inside of the range of data values. If you look at possible values for the above ground living area, we have all the way from 334 square feet up to about 5,600. So I picked a value near the middle at about 2,500, kind of an average number of square feet. And we want to try to predict the price based off of that number of square feet. So basically what that means is if you were using this line in the green and you were at 2,500 square feet, which is, if I change this to green as well, that is about right here. That means what price is at that point. So if we're at about 2,500, I think my point was a bit off, so let me try redrawing it. What would be the price? To me, it looks like about maybe $270,000. Of course, I'm just guessing right now using that green line. How we actually get the real value is using the equation of the line. What the equation of the line says is you take the slope, multiply it by the x, the area. That's the value I gave you, but this could be any number. And then you add the intercept. You can use these values or you could use the ones calculated here. You'll get the same answer. What's important is it has to be slope times the value given plus intercept. That is the equation of the line. And I guessed about 270,000. It's actually 286,394.92. That would be the price for 2,500 square feet, sorry. The nice thing about using the equation format is that you could actually change the number as well. Like if you only had a 1,000 square foot house, the price would update based on the equation. If you have a 3,000 square foot house, the price that's estimated would update based on the equation. So by using the equation format, you can actually change the value given for the living area and see what your predicted price would be for the sale of the house. All of those values, 1,000, 2,500, 3,000, are within that range of data. But what if you want to predict outside of the range of data? Remember I said that the highest living area we have is about 5,000 square feet. What if we wanted to make a prediction for a house that's 50,000 square feet? And this is actually a real house that I chose. It's like Drake's mansion in Toronto is estimated to be about 50,000 square feet. So let's see if this data predicts or what it predicts for the price of the house. So again, you'd have to take slope times value given for the x, that's the area, plus the intercept. And that is the equation of the line. Press enter. I don't have enough space here, so I need to make that cell bigger. And it's guessing $5.4 million approximately. This actually is not accurate. I think Drake's home is valued at like $100 million when I looked it up online, not only 5.4 million. So this is not accurate. And the reason that it's not accurate is because this is an extrapolation. It's far beyond the data we have information for. We only have information for just over 5,000 square feet. So the line is not making an accurate prediction for 10 times that at 50,000 square feet. So you can really only be accurate for your predictions within the data range, not far beyond it, like we have for Drake's mansion here. It doesn't take too long to find the slope and intercept, so I do want you to try a learning check question. What I mean by that is for the example we've been looking at with sales price and enclosed porch area. So that was this one here that had a weak relationship. I want you to try to find the slope and the intercept using both methods, and then make a prediction for any porch area and what the price would be. Please pause the video here, and when you press play again, I'll show you the answer. So thank you for trying the question. If you use the equation method, you would have to use slope for the slope, and for the y's, you'd select the price. For the x's, you would select the porch area. And you should have got a slope of negative 167.13. For the intercept, same order. The y's have to come first, so that's the sale price. And then the x's, which is the enclosed porch area. That gives me 184,590 and about 30 cents. So if I want to interpret these values, they're very similar to before. Just instead of saying when above ground living area increases by 1 foot, this one is when porch area increases 1 square foot. The slope is how much the price will change. Because it's a negative number, this actually represents a negative correlation, meaning the price will actually decrease by $167.13 when you have increasing porch area. So apparently having a big porch actually decreases the value of your home, maybe because it's an older feature and people now don't typically have porches. The interpretation of the y-intercept is when the x value is 0, what is the price? So here the x value is the square foot of the porch. So when porch area is 0 square feet, how much is the price? Price is the value of the intercept, 184,590.28. So getting close to $200,000 when you do not have a porch. If you use the regression tool to get the same results, I would go to my data sheet. And then from the data sheet, I would go to my tool pack and regression. I want the same Y range as before, but for the X range, you'll need to reselect that. So I just erased it, and I'm selecting my new enclosed porch area. Then I'm going to let it go to a new worksheet, and I'll copy and paste this into my regression sheet. Notice that the numbers are the same for the intercept and the slope that we got here. If you want to use them for prediction, choose a porch area. Maybe I'll do like 100 square feet. And for predicting the price, you'll always do slope times the value you selected plus the intercept. You can again use the slope and intercept here or the slope and intercept here because they're the same numbers. Press enter and you get a predicted price for that porch area. You could pick any number here since I didn't specify. I would recommend doing an interpolation. What I mean by that is the lowest value we have for porch area is 0 and the highest is 552. So I wouldn't recommend going above that. But if you did 200 or 100 again, you can always switch up what value you did and your price formula should automatically update. So that is how we use regression to get the slope and intercept of a line. And then once we have the slope and the intercept, that's what you need to get the equation of the line that you can use to predict the value of one variable based on another. So again, looping back to our Ames housing data, how does this help us get closer to answering our key question? So learning about regression, based on the analysis, which factor do you think they should prioritize for pricing and marketing? That was part of the original question. Well, porch area actually decreases price, so definitely not that one. But above ground living area does increase price. So if you have good above ground living area, your price would definitely increase. So between these two, above ground area is definitely the one to prioritize. But we didn't do the regressions for every single variable because that would be quite time consuming. You'd have to do all of the different relationships like we have in this correlation matrix, like maybe sales price with quality, sales price with year built, to actually see the impact of every single variable. If a homeowner could only improve one feature, which improvement would you recommend based on the regression? Again, between these two, having a porch decreases price. Above ground living area increases price. So you might want to say if you have a porch, maybe you should actually increase it. You could increase the value of the house by converting the porch into actually part of the house, part of the living area, or maybe just demolishing the porch and getting rid of it altogether. That could be some recommendations based off of these analyses. Again, you'd have to look at all of the variables individually, like overall quality, year, etc., to actually know how all of the features impact selling price. But for these two we've analyzed, you could say get rid of the porch because it decreases value, or better yet, convert your porch to actually full usable house space that's considered above ground living area. That will help you to increase the price. So the main purpose of finding this regression equation is so that we can actually have a mathematical formula that we can use to make predictions for prices based on given values for independent variables like porch area and for living area above ground. Thanks for watching this video. If you have any questions, please reach out to your professor. And there is one more video in this lesson on other nonlinear models. Please go to the next video to finish off that last part of the learning outcome. Thank you.